Hi, and welcome to eCHO. This is the 121st episode. It's my first one of 2024. Is it your first one this year as well,
Yes,
Dan?
it is. My first episode, 2024.
Fantastic. So welcome, everyone. As always, if you're watching, do say hello. We love to know where you are and what you're up to. I can see a couple of people already. Help me, please. Hello. We're going to need that. And Rafa, good to see you. So we don't have a huge amount of news to cover today before we dive into the main topic. Hello to Davy, one of those. Sorry if I'm mispronouncing. And hello to Doc. Lots of people watching today. Good to see you. Yes, so we are about to dive into some kind of coding challenges that we each took on over the holidays. And, I think we both learned quite a lot of things. So hopefully we can share that.
It's been an exciting journey over the holidays.
Yeah. Before we get into that, we do have one little headline that we should really share, which is that the schedule for Cilium and eBPF Day co-located with KubeCon and Cloud Native Con. I think that's its full title. The schedule is now live, and that's happening in Paris in March the 19th. So that's the day before the main KubeCon schedule kicks off. Lots of really great content in that schedule, so do check that out. If you're going to the co-located events, you can buy an all-access pass, and then you can come to whatever takes your fancy from Cilium and eBPF Day. If you can tear yourself away from that, you might want to go and check out some other colos as well, but obviously we don't advise that. Stay at Cilium.
So the co-located events day is just so action-packed these days as well. It's absolutely fantastic. There's almost as much content kind of squeezed into one day as there almost is in the rest of KubeCon at this point.
Yeah, there's some fabulous people, some fabulous topics, and all kinds of good things on this schedule. So I am very much looking forward to that. And a few more people have said hello. So hi to our good friend Marino, and hello to Shadrach. Good to see you. And Alexander, welcome to all of you. All right. So shall we start with Advent of Code?
Let's go there.
All right. So I'm going to guess that most people have some familiarity with Advent of Code, but I'll just sort of mention it a little bit before we dive into the eBPF adventure that I had. So Advent of Code gives you these coding challenges. You get sample input, so I think not everyone gets exactly the same input. You can't progress from one challenge to the next until you have to solve each challenge in turn.
Do they unlock them? Is that how it works?
Yes, they do. Yeah,
okay.
I have a feeling if I go back to the main page, I might be logged out, so I won't do that now. But you get like a kind of advancing ASCII art picture as you go through from one day to the next. And there's always a sort of slightly oddball backstory about, I think it's nearly always about like Santa and elves and gift delivery and crazy machines and things that get in the way of the elves and what have you. And to be honest, I'm not sure the backstory is necessary to solving the problem. But what you get is you start seeing some sample input here. So here's like 4 lines of input, and they're telling you what the challenge is. So in this example, they're saying you need to take the first digit and the last digit in every line and turn that into a number, and then you add up all the numbers. So as you can see here in this example, the first line has a 1 and a 2, so that's 12. The second line has a 3 and an 8, so that's 38. The third line, there's a few extra digits, but the first one is 1 and the last one is 5, so that's 15. And the last line here, there's only 1 digit, so that counts as the first and the last. They're quite good usually at giving you enough examples to cover the edge cases. So that's fun. And I guess I've done this A few times. I don't know if I've ever made it all the way through the whole 24, 25 days, but I have done it a few times to keep my hand in on different
Yeah.
languages. One year I tried to teach myself Rust by doing this, so it's kind of fun thing. And yeah, I decided that it would be fun to see if I could do it in eBPF this year. And one thing that is I would say a kind of classic thing that happens with Advent of Code challenges. This looks fine because it's like 4 lines of code, but the actual sample input, which I'll show you, well, actually I could show you it now. It's much longer. So it's 1,000 lines. I think if I word count this, yeah, we can see it's 1,000 lines long. And sometimes they're like 10,000 lines long or crazy amounts long. So
Wow, okay.
Quite often the problems are designed to be, you have to have an efficient algorithm, not just any old algorithm. Otherwise you run out of time, like in the universe. So the other thing I kind of wanted to do when I committed to myself that I'm going to try and solve at least one problem in eBPF is I wanted to have it. I didn't want to be using user space for any of it. So I wanted to say, you cat the file or you edit the file, or somebody opens the file, and that should be sufficient for eBPF for me to write an eBPF program that will spot the file being read, take the input, process the input in whatever way I need it to, and then spit out the answer. So that was kind of the quite a lot of this challenge really involved reading the file in the first place. Actually processing it was not really that hard, relatively.
I mean, it's impressive that you took a challenge which is already quite tough and decided, well, it's quite tough, but how can I make it even harder for myself?
I wanted it. I think for a while I've sort of had in the back of my mind, I never really done anything with files, so this seemed like a good opportunity. So the first bit was, how am I going to capture those file read events? And I'm sure lots of people watching will know, you can hook eBPF programs to kprobes. You can always, there's a newer alternative called fentry. I'm on an ARM machine, and fentry isn't implemented on ARM I think it's like kernel 6 and above that do have fentry support for ARM, but I didn't have that. So I've just got kprobes. So if anybody's going like, why is she only using kprobes? That's why. So my first thought was, okay, great. I'm going to spot when somebody is reading from the file I'm interested in. So if I find in my code the read, this is my kprobe that happens on read. Now, at this point, I do get a file, but I wasn't really, I guess I wanted to not intercept every single file read that's happening on the whole system. So what I decided to do was to keep track of opens as well. So if I find VFS is virtual file system, so that's the kernel function that does a read. I find my open function. So when you in the open call, you do actually get the information about the path of the file being opened. And so what I decided to do was to say, I'm going to look at the current task. I probably didn't need to do this bit, but I decided I would. And look at the current file name. And I've got a map for file names I'm interested in and executables that I'm interested in. So that allowed me to very quickly skip over file reads that were not related to files and executables I'm interested in. And I did allow myself to populate that map from user space. So in here somewhere, I've got Okay, some commented out code. And yeah, so I said I'm interested in cat. I probably could have also added more in there, and then various different files that I was using for different examples of Advent. So that allowed me to not have my debug absolutely crazy full of thousands and thousands of events. All right. So if I go back to my read, oh, no, wrong window. There we go. Read. So I basically look up in a map to see whether or not there is an entry for this current process, and I've populated that map with this process ID if it matched the executable and the file name that I'm interested in. So I'll go, okay, great. I've started a read here, and then I have this state. So the read call is going to give me a buffer, and maybe I should run it to show some of the trace. Will it trace out the length? I think it will. Yeah, it will. So I'm just going to make my part 1. So that's giving me all the output from the verifier, and then this is where my output is going to arrive here. And I think if I just do BPF program trace, actually let's do, just so you can see all my different programs. So there's my read. I've also got something attached to the return from read, which we'll talk about. I've got close, I've got open, open, and I've got something here called buffer read, which we will definitely look at. So if I do trace, so we'll see all the trace that's coming out. And if I cat the whole full thing, it's going to show the result at this point. No, it's got the result wrong. I've done something wrong. What have I built wrong? I think I know what's happened. Okay. What you can see here, though, is like the size of that buffer. And I think this was one of the first things I traced out, was like, okay, that's a large number. Like, there is no way I'm going to be able to parse that whole buffer size with like the limited stack that you get on BPF, which is
pretty minuscule, to be quite fair.
Yeah, I meant to look it up before I came on because I'm terrible at remembering numbers. But yeah, so I could pretty quickly see I'm not going to be able to just parse all of this data in one BPF program, or at least not. So I thought, okay, what are my options? How can I didn't think it was going to necessarily be this whole buffer size, but I knew it was going to be, thousands of bytes of entry, because I knew the input was going to be 1,000 lines long. So, okay, how can I break this down? So what I do here with the read sets up this buffer state where I'm going to keep track of things like what my running total is for the A state, means Advent state. And this is like my running total that I'm trying to parse out of the file. I've got the number of lines that I've parsed, because I just wanted to be able to output how far through these thousands of lines I am. Yeah, the first digit and the last digit if I'm midway through parsing any given line. So in the entry to the read, I've set up this essentially a state variable. And then I've also got when I come out of, so this is the rep probe. So this is at the end of the read. So now at this point, the buffer is full of data. So I check whether it's a event that I'm interested in, and then I get my my state information. And this is how I started doing sort of breaking things down. I thought, oh, I can recurse through a number of tail calls, and I can process using this function, which I've called buffer read, and I can process a certain amount of data, and then I can call that tail call again, and I can call it again, and I can call it again. So that's where my buffer read comes in. Hopefully, there we go. So actually, maybe it's worth this. So I can set up this program array. This is how you set up tail calls. Called it tail calls. I've only got one tail call that I call some number of times. So every time I call this function, I'm going to read the current state. This is my sort of buffer state. And then I'm going to loop through so I'm going to copy. Actually, where's the copy gone? There's a copy somewhere. Here we go. So location is the current point in the buffer of like data that's being read. And I'm going to read it in chunks. And my chunk is a maximum of this advent buffer len. And this is something that I just adjusted by trial and error to see how many times I could, how big I can make that buffer. Because if it's too big, I'm going to bust the stack. And
So, I mean, a quick look, but the stack is limited to 512 bytes. So it's it's a bit like programming the old days.
I nearly said I thought it was about 500 bytes, and as I was thinking, I thought that's too small, surely. But yeah, no, it is really small. So I'm gonna. Again, I've also got a loop here that again was trial and error. How many times can I go through this loop of reading a chunk of data, and then so here's another loop, BPF loop. BPF loop is well, I've got this examine char. So examine char is going to be the function that actually looks at individual characters and parses them and decides whether it's a digit or not, what have you. And so this was one of the first things that I really learned here was you can't pass map data into a loop.
Oh.
You could, I think it has to be stack memory. So I had to, there were times where I was experimenting with this where I was like, oh, can I just pass in the current buffer state? And no, you can't. So back here, this is why I've got a copy of my current state going into the loop. That's going to just do its parsing and update the current state. And then I have to copy that back into the map again, update the map. So I'm just, every time I go through this buffer read thing, and if I've still got more data to go, I'm going to do a tail call. Another thing that I had come across before, but was kind of, interesting, was you can do 32 tail calls. And if you attempt to do 33, it will just not happen. But it doesn't complain at you. Like it's not like the verifier will stop. It will let you attempt.
So it just silently fails, though.
Well, it silently succeeded. So the only way I knew whether or not that was happening was by looking at tracing to see whether or not where I was tracking the number of lines. I could say, oh, it hasn't passed 1,000 lines, and therefore it's telling me it's trying to do the 33rd call. That just didn't happen. Yeah, I need to adjust this. Yeah, so where am I at? Yeah, examine char. So examine char was like super simple. Where is it for? I'm not sure I've even got the file open.
I quite like in the comments, if I just quickly bring up this, that somebody was doing something similar to parse DNS response messages in the kernel.
Oh, my friend Daniel. Yes, great. Ha. Yeah, brilliant. So yeah, for part one, it was super simple because all I needed to do was look at each individual character, decide if it was a digit. If it was a digit, I could, keep track of that as either the first digit or the last digit. And if I find a new line, then I know I've got my first and last digit, and I can turn that into a number and update that as I go along. So that part, like the algorithmic part for this, was pretty simple. The much more tricky bit was tuning the number of loops I had to go through.
Yes, yeah.
I think I might have failed to make this properly, so I hope I hope if I rebuild it, it's actually going to work. Let's see. So if I do the example first, let's clear this. Actually, let's also just tidy this up and bring up the trace. Okay, yes. So I've done this so many times, I know that is the correct result. And yeah, I didn't have to do any tail calls by the look of it in that version, but if I do the full content, then yes, I know that is also the correct result.
Very
and there's
impressive.
my depth is my number of tail calls.
So levels of recursion pretty much happening here is amazing. I love it.
Yeah, it was quite fun. I think the only other thing that it was maybe worth talking about was for part two, where as well as looking at individual numeric digits, you had to do the same thing, but sometimes the number would be written out in characters.
Oh, wow.
So you have to sort of parse where you are in letters. And sometimes, I wonder if I can quickly see an example. You get examples where I can't see an example on the screen.
Second from the bottom, I can see 7.
Yeah, there's 7. Yeah, but sometimes you'd see things where it might start off with one number and then go. So imagine that in the second E, after that, it said, well, no, even better example. So imagine it says 7 and then it's followed by INE. So it's actually got NIN. So it's actually got 9. So you'd have 7 and 9 kind of overlapping.
Right. Okay.
So, just you had to have your wits about you a bit. And the first way I did it was the kind of obvious thing of saying, I'm going to look at every single character. And if it's an E, then, well, that could be, the third character in 1, or it could be the third or the fourth character in 3, or it could be just if this, then whatever, just stepping through all the possibilities. I thought, this is quite boring. It's not exciting code. And there's a lot of branches here. So this is a lot for the verifier to kind of get through. So my other implementation was to do it as a state machine. I did allow myself to populate the state machine in user space. And I don't know if this is going to show up brilliantly. Yeah, my
wow. Yeah, that's
it's grey on grey, so that's not brilliant. Yeah. Essentially, this is a state machine saying, maybe people will just have to look at this on GitHub later. But essentially, if it's basically saying if your current input is one of a certain set of letters, there's only so many kind of next numbers that can relate to, and you can be in, let's say you're in, I can just about make this out. So having an E is possibly the first letter in 8. And if you got an I when you're in that state, then you're still potentially progressing through the word 8. And after that, if you've got a G, you're still potentially progressing. Anything else, you're not. So I set up this state machine. And then the code for implementing that is super simple. It's really light. So basically, I just look up based on the current state and the current input character, I just move to the next state. And that will tell me whether or not I've found a number or not. And then also parsing digits the same way. So this code is almost exactly the same as what I did for the part 1. That was
very nice.
And that allowed me to have I could use a bigger buffer length because there was less complexity in the parsing. So yeah, that was my Advent of Code challenge. There's one other part, but I think maybe we should talk about your code, and then we can come back to my my sort of next step thing.
It's funny the loops and the minimal amount of data that you kind of have to play with and things like that are pretty much almost identical to some of the problems that I had. In most of the cases, I was just like, instead of doing loops, I'll just do it, repeat the code 3 times until I've got enough information that I'm actually after. So my code is definitely not going to be anywhere near as elegant as that. But
I think that the elegant bit, I was pretty proud of the FSM, but everything else.
Yeah, no, it's amazing.
It's beautiful.
Yeah, so over the it was on a train journey, actually, with nothing to do other than my laptop and a virtual machine. And I decided to start playing around with what's actually inside the packets that we're kind of flying around. I think if you look at kind of a lot of the examples with eBPF at the moment, and a lot of the use cases in the network space to a certain degree, a lot of it really is kind of focused on the layer 3 and layer 4 aspects of it to a certain degree. So looking at IP addresses and looking at ports, and then doing redirection or dropping or natting or things like that. There's been ongoing work now to look inside the actual data side of things. So Tetragon, for instance, has kind of HTTP parsing, DNS parsing, and some other parsing things like that. But I decided I kind of wanted to have a go at doing that myself from scratch and kind of see how difficult it was. So I think what I'll quickly do is step through what that actually kind of looks like. So when we attach a program to either XDP or to TC, so ingress traffic control, we effectively have to do a number of things. So we will get a socket buffer, which effectively is just a lump of data. We don't really know anything about it at that time. So inside that socket buffer are a number of fields that we can make use of. Data is the pointer to the beginning of the data, so we can see here, and data end is the pointer to the end of that buffer. So we know where it starts and we know where it finishes. Now we need to try and work out what it actually all is. So what we tend to do is, if you look at this first line here, is we will cast all of that data to an Ethernet header. So we effectively, as far as that data, we've now made it look like an Ethernet header. We can now look inside that, so we can basically look at the protocol of the frame. And if that all makes sense, it will basically tell us what's inside the rest of that. So we can basically look to determine if it's if it contains an IP header. So if that is the case, we can kind of move on. We will create a new pointer, which is beyond the length of that Ethernet header. So we know how big the Ethernet header is. We're starting from data, so we're now at this point. We've now cast the rest of that data to an IP header, and we can look inside there to determine if it's set to be TCP inside it or UDP or whatever. With that lookup, we can then basically move on to the next side of things, where again we will point the next point. So we start at the data, We've got the size of the IP header that needs removing. Oh, that should be size of Ethernet actually. So we've now looked at that point. We're now looking at the beginning of the TCP header. We can look inside that TCP header. We can get the source ports and the destination ports if we need those. One thing that I wasn't aware of to begin with is that the TCP header can be variable length. So sometimes we may need to actually do some maths to determine the size of the TCP header, just so that we can then determine where the rest of the data actually begins. So with all of those bits of information, we can get these two bits of information that we typically need. So like we had the pointer to the beginning of the all data and the pointer to the end, so the data end, we'll create a new number effectively, which is the size of the Ethernet header plus the size of the IP header plus the size of the TCP header. So we're now pointing at the end of all of those headers. And then the P length, which is the packet length or the processed packet length. So this is how long that application data actually is. So if we kind of quickly show what that looks like. So as I mentioned, we have all of this raw data. We don't really know what it looks like. We've now worked out how big the Ethernet header is. We've worked out how big the IP header is. We've worked out how big the TCP header is. So we now know at that point, we have the offset of where the rest of the data is, and we have the remainder of the length of that. So we have the two bits of information that we kind of need in order to start processing those bits of information. So we've stripped away layer 2, we've stripped away layer 3, we've stripped away layer 4, and we're kind of now left with, well, layer 5, 6, and 7, but just think of it as layer 7 for what we're going to be talking about. So now that we have that, it's a case of turning that into something useful. So there's been a couple of different protocols that I've kind of looked at trying to parse. And some of the protocols, I mean, a lot of the protocols were kind of implemented kind of the golden age of the internet and the golden age of networking to a certain degree. You know, a lot of people are used to kind of dealing with JSON and YAML and things like that. You get a lump of JSON and you don't have to worry about how big the strings are or how it's kind of organized. You know, the mappings of JSON kind of take care of all of that. A lot of the, you know, the architectures of kind of these protocols in the early 90s and things like that, it was, yeah, every protocol is defined differently. And
I remember some of this.
Yeah, some of them require a lot of back and forth to determine, yeah, kind of what things actually look like and whatnot. So understanding protocols. There's a couple of different ways that you can kind of go about learning about how these protocols, how they're architected and what they look like. So RFCs, and these are called request for comments, but effectively, back in the day when everybody got their heads together, they would define these standards in these request for comments documents. And, you know, once enough comments were had, they decided that that would then become the standard for these particular protocols. So these standards effectively determine the organization and the structure of the data. So RFCs are, you know, the architectural documents that detail what these actually look like. So there's an RFC for HTTP. There's an RFC for DNS that I believe Daniel mentioned earlier, and that defines, you know, RFC message, DNS messages look like. Same with BGP, same with other protocols. Additionally, another useful way of kind of looking at what those protocols actually look like is having that traffic flying around and doing things like TCP dump and then viewing that in tools like Wireshark. That will give you effectively what we're looking at now, but you can kind of pull it all apart. And Wireshark understands protocols. So it will tell you that these 4 bytes mean this and these 2 bytes mean this. And with that information, you can then turn that into something that makes sense in eBPF. So that's kind of the structure of things. Now we need to turn our, you know, our ones and zeros from our offset into something that actually makes sense. So the first example, and I'll just stop sharing this screen and move on to another screen. And if anybody has any questions about what I'm talking about, please do feel free to ask, because I may step over things that may seem irrelevant to me, but could be very important to yourselves. So let me see, can you see this? That's the wrong one. There we go. Let me make this a little bit bigger, but this is code for HTTP parsing. And so, as I mentioned, if you look at this line here, we've got the TCP header. We're going to now
lots of checks to make sure that we're not going off the end of the data, because the verifier requires us to explicitly check that every time.
That is a good point. Yeah. So you can, normally you would just get this data and say, I want this data to look like that. If you're not performing checks to make sure that what you've done hasn't gone too far and things like that, the verifier will let you know by not letting your code actually run. And it does this in a load of different places as well. So it can kind of be easy to miss these sorts of things out and all of a sudden start getting kind of quite spurious errors. You have to bear with me a little bit because I wrote some of this a while ago. So right, here we are. So this is the bit that actually makes sense. So at this point, we have worked out the length of the TCP header. We've calculated the offset, so we know where our HTTP data actually starts. We've created a buffer on the stack. Got to be careful about how much data we're actually going to allocate on the stack, because as we mentioned, there's only X amount of bytes in order to do that. So for what it is that I'm going to be demoing, 60 bytes is largely enough for us to grab most of the HTTP header and kind of parse that header. So what we're actually going to do is now we're going to use a BPF function, which is called load bytes from socket buffer. So we point to the socket buffer itself. We point to the offset, which is past all of those headers. We specify where we want that data to actually go. And we specify how much of that data we actually want to load from the buffer into our variable on the stack. At which point then we can start to parse the standard. So the HTTP standard is actually, it's simple and complicated. It's simple in that it's a very simple format. It's complicated in that it's completely dynamic. So your URL length can, I don't know if there is a standard for URL lengths, but some URLs are absolutely hugely complicated, and there's things embedded in URLs and things like that. So, if you're doing quite complex parsing, you're going to need to think about much bigger buffer lengths in order to parse that. But we're going to be doing simple paths here. So the first thing that happens when you do a get or when you do a HTTP request is you have the verb that is sent first. So the first thing that happens is it's all in text. You get a get in capital letters. So we will check the first 3 characters of that buffer to determine if it says it has the verb get. If that is the case, then we will create another buffer in order to store that URL on. We will then look from the 4th point. So get is the first 3 characters. There is a space as part of the standard. And then the rest of that line is the URL. So we will step through all of that data. We will put all of that data into the buffer. So we've now we've checked that there's a get, we've gone over the space, and now we've parsed the URL path. We've put that URL path into a variable on the stack. And what we've actually done here as well is, now that we have that path, we've got the length of it, we can use maps. So at this point, we're adding the capability of saying, from the user land, we want to actually have an action that's performed should we actually find this URL as part of a map. So we're pushing those URLs into maps for us to actually look at. So we do a lookup based upon the path. If we find that map, then we've basically parsed the the HTTP entry that's actually going through. So this is kind of quite a simple use case for being able to determine what's actually happening as part of gets. We can easily add the other verbs in there if we wanted to do those sorts of things. And this is basically just doing simple path matching for HTTP. So we can quickly kind of demo what that actually looks like if we bring up another window. So in this window here, so what we're doing, we're building the program. We are starting it with root because it needs to, oops, I forgot to bring my screen in.
It's all right, I'm there.
Thank you very much. Yeah, so we built our code. We've built the user land side of things. We have started it with root privileges because we need to load the BPF program. It's attached itself to our interface, and the path that we're going to be looking for is /test. So every time anything is going through that sits on port 80, we will randomly, something's done a HTTP request on my development machine. Let's look here. So we can see here, it's found that a path has come on. It's determined how long actually, it's parsing HTTP headers at this point. We did a get. We can make that actually a little bit easier to understand because we can, so this is actually what sent. That is the header that is sent to our eBPF program over the HTTP protocol. eBPF will get that data. It will read get, which is the first 3 characters. It will then go to the 4th character, and it will parse all of this for the next space, which is the protocol for HTTP. Because we've got that map, which is looking for test, it will do the same lookup. But at this point, it's actually found, it's done a map lookup. It's compared the URL that's part of that to what actually exists within the map. At this point, we can start to infer more logic. So for instance, if anything was trying to do a get on /etc password, there was exploits years ago where you do full paths. So you can do ... /etc. So you get all the way back to root and then get that etc password off the URL and things like that. So we could start to put logic in there and do almost a HTTP based firewall, which determines what is and isn't allowed based upon rules that we could push as part of maps and things like that. There's a quick question from somebody, which is, I suppose the mileage will differ significantly for HTTPS requests. 100%, yeah. I don't know if Liz wants to kind of cover that.
Well, so if it's HTTPS, I'm not quite sure how much of the packet will be, well, actually, no, the whole thing will be because it's encrypted from TCP layer. It's TLS. It happens at TCP layer. So yeah, the whole packet would be encrypted. So you would need access to the key in order to decrypt the packet before you'd be able to parse what's going on inside an HTTPS packet. Now, if you're the endpoint, that might be a reasonable thing to be able to get hold of. But if you're kind of man in the middle, hopefully you can't get hold of it.
Yes, yeah, absolutely. Yeah, so HTTPS requests, it's text basically. It's quite simplish-ish to kind of parse. What you do with it at that point is really dependent on where you sit in the stack. So one of the things that I wanted to try and do is if I see a URL if I see a path for this, send that request to a different backend server. Now in my head, I thought, right, well, I'll just change the destination IP address based upon the URL. I'll give it like 10 seconds or so just to see if anybody could work out why that actually wouldn't work.
I know why that won't work.
Yeah. 3, 2, 1. So Liz, if you want to hazard a guess as to why.
Well, so going back a couple of eBPF summits, I did a a load balancer from scratch, which is a sort of similar idea of taking packets and looking at their contents. I wasn't going as far as that HTTP protocol, but I was essentially doing like layer 3, 4, well, 3, isn't it, IP, just load balancing across different containers. And you have to get not just the IP address, but also the MAC address correct in order to get it to to get to the destination that it needs to get to. So you'd take an incoming packet, change the destination IP address, but also change the MAC address, and that would work.
So this was slightly different. The issue that we were having here is basically when curl is sending a connection, it sets up a TCP. There's the ACK, there's the SYN, and we start to have those ACK and SYN numbers. If all of a sudden I send another request that's already been ACK and SYNed to a different server, the handshake has never actually occurred.
Okay.
It's just suddenly got this GET request, and it's like, who are you? Like, you've not even said hello at this point. So no, I'm not sending you any data. You'll just get a reset packet back because it's like, I don't know who you are. Stop. Unless you're saying hello first. I'm not. We're not going to do a proper connection, things like that. So that was kind of a bit disappointing. I thought this is going to be quick and easy, but no, there's nuances that are a part of the TCP stack. So quickly, I'll just kind of cover one of the other protocols that I quickly did recently.
I guess, if you did sort all those things out, that's essentially what an ingress is doing, right? It's taking an HTTP packet, it's looking at the contents of that packet, or looking at the headers and deciding what backend service to send that to. So yeah,
absolutely. But the problem is you're going to have to maintain some level of TCP state inside the inside eBPF, which is beyond my level of expertise. So you need some way of doing a secondary handshake to one of the destination servers before you then send that prior request over. So this is the other one that I looked at doing, and this is basically doing BGP. So this allows us to understand BGP messages that are taking place. So for those that have never come across BGP, it's a protocol that's used everywhere. It basically is what binds the internet together, and the protocol, it largely allows one network to tell another network, I have all these IP addresses or these IP ranges. So if you want to get traffic to this particular IP range, send traffic to me being a router that's BGP peering. It's an old technology. So the protocol is 30 years old or so, I think. Very simplistic, TCP based, not UDP. And it uses a concept of messages. So it's relatively straightforward, but it comes with its own nuances. But it's the same sort of thing. So we get the offsets, we get the lengths. Let me shrink this bar down because I don't need all of that. And then effectively, as long as we know that the length of the packet is more than or equal to 18, which is the size of a BGP message header, we can then create a message header, which is based upon this struct, which matches the RFC, and we can copy those bytes over. This all seemed relatively straightforward, but it didn't work when I first did this. And the reason for this is struct padding, which is a very helpful thing that the compiler does. So, yeah.
So back in my youth, I worked on network protocols in C, and yes, structure padding is. We were implementing network protocols in a sort of portable way, and one of the things you needed to do was absolutely. You needed to know about structure padding, and you needed to account for structure padding in every single structure and make sure it would be identical on every machine, which is
So the BGP message header is 16 bytes. It's a 16-bit integer and an 8-bit integer, which equals 19 bytes. However, when I tried to do the load bytes based upon the size of it, it would error every time. I'm like, I know there's 19 bytes there. It says on my window that it's 19 bytes at this point. However, after pulling my hair out for a while and I let this hover, it said that my struct was 20 bytes. I'm like, but it's not, it's 19. I can see that it's 19. The compiler had decided to add an extra byte to round it up, basically, so that it made more sense. So because it had done that, I was trying to read 20 bytes out of 19 bytes, which is impossible. So things were erroring. So in order to do that, we need to have this, which basically will pad to a single byte as opposed to rounding things up to make things bigger. But that was a waste of a couple of hours. It was like, why is this not?
The reason why they do that is to have integers normally aligning with a sort of natural boundary, you know, so that you're not having, I don't know, 4-byte integers sort of wrapping from across the sort of natural boundary of memory. So yeah, typically if you've got like, say if it's a 32-bit machine, you had a 1-byte value followed by a 32-byte value, 32-bit value, the 1-byte value would have 3 bytes of padding following it to get it to a 32-bit boundary. Yeah.
Which, you know, makes sense, but not when you've got exact figures.
If you don't know, you don't know.
Yeah. So I'm quite happy that VS Code kind of like just popped up that message. I was like, oh, that's annoying. I'm glad you told me that though. But yeah, so effectively, as I mentioned, if you look in these RFCs, it gives you a diagram of what that message should actually look like, which is, I'll get the header up so you can see what that kind of looks like. But yeah, so this is, we get the marker, which identifies this as a BGP message. We get the length of the rest of the BGP message, and then we get the type. So there's a couple of types of messages that will go. But yeah, BGP message, as you can see, without it, it says it's 20 bytes. But 16 plus 2 plus 1 does not equal 20, which is very annoying because it's padded it there. So anyway, that's one thing to be aware of. So as I say, in the code, we grab those bytes from the rest of the buffer, so from the offset. Once we have all of that, we now have our BGP message, and we can basically do a case statement based upon the type of message. Now, if it's a keep alive message, there's no additional data. This is just a message that is sent every few seconds so that the connection is alive. The other messages that are of any sort of real importance are open messages, which are the initial connection, and then the update messages, which are, here I am updating you with a bunch of new routes that are now actually available. So it's the same thing here where we needed to create some new structures based upon the RFCs that we could then copy the rest of that message into so that we could actually understand what was actually happening as part of the BGP message. So effectively, taking the RFC, we now have implemented enough code in our eBPF program for eBPF to be BGP aware. So it understands that not only is there data going backwards and forwards, we actually know what that data is. We can see that these are BGP messages. We can see that these BGP messages are of a certain type. And we can actually pass further into those BGP messages. So we can see things like what routes are actually being sent back and forth, what our AS numbers actually are, and things like that. So yesterday, a friend of mine challenged me to actually basically do a bit more of a BGP firewall kind of thing. So we'll do a quick demo now of a machine peering with a top of rack router, sending some routes over there, sending a single route over there, which is fine. And then we'll basically talk about why you may not want to do that and how we could change that into something else. So quickly stop sharing this. And this will be my last window being shared. Share screen. Right. So this is my terminal. Down at the bottom, we will start my code. So I forgot to bring my screen on.
It's all right. I've done it.
Right. So what we're going to do first is we will start my code. So it's doing two things here. It's building the code. It's building the userland code, and it's going to start the program basically. So if we just quickly look here, where are we? There. So building the code and then running it and binding it to an interface. We can now see my userland code does two things. It injects our eBPF program. It attaches it to the TC, ingress, and egress. It will also start some eBPF userland code, which is going to appear with the top of rack switch. So we can see, I know it's quite wordy here, but we can see here that my BGP program has appeared with that top of rack switch. What we can also see in these eBPF trace messages that we're actually seeing what's actually happening here. So we can see that there's a BGP open message. We can see the AS numbers and we can see the identifier numbers. And then our userland code has actually brought the peer up. And now in eBPF, we can actually start to see a lot more information. So we can see there's an update message that's been sent that's 48 bytes long. We can see that there's 20 flags, 20 bytes worth of flags. So we can pass all of that information. Some of that is going to be the AS numbers. That's part of the option 2, and option 3, I think, is some additional routing that may be needed. The final part of the update message, which is important, is the route itself. So this is the route that is being pushed to that top of rack switch. So if we pop to the switch, we can see that that route has been passed as a destination. And to get there, we go through the machine that is actually peering with. So if we kill that, we should now find that there's no routes available. The peer's been removed. And for the final thing, what we're going to do is we're going to use our eBPF code. And when it passes the NLRIs, which is the network information, it will do a lookup. It will do a map lookup to find this particular path. And if it finds it, it's going to replace it with this path. So our peer still thinks it's sending .2, but the top of rack switch is actually going to receive a different route altogether. So we're effectively patching things on the fly. So now if we do the same thing, code's compiled, code's running, the peer should come up in a second to the top of rack. So up it comes. That's strange. There's no BGP messages.
Huh.
But it has worked. That's odd. Okay, the code has worked. I just haven't gotten any logs. But we can see here, originally the path was .2. And it's been patched to .3. So we've actually changed in flight the routes that are being pushed to that top of rack switch. So this effectively allows us to modify the behavior of BGP without network administrators having to do anything. So we can control the behaviors. We can patch, we could block, we could change. There's all manner of different things that we can do. So that's BGP now. That's eBPF now BGP aware. We can control anything that's happening between routers, regardless of what it is that's taking place.
Very cool. Very nice. We got a good question in from Siddy. Hi, Siddy. How can eBPF in the kernel impact routing on Linux machines or containers? Well, let me count the ways. I mean, so Cilium is very much using eBPF to route traffic between different containers, do things like load balance across different backend containers for a service. So there are, and I mean, that's just one example of a project that's using eBPF very much to manipulate network packets to build an entire kind of networking solution. eBPF in the kernel, you get to manipulate any network packet that you want to if you so choose. So they're really, the sky is the limit on what you could impact using eBPF, and essentially it means that more and more we can push networking capabilities that have currently typically been implemented in user space, we're more and more able to push those into the kernel where they're super efficient. And yeah, that's, I think one of the, certainly I think it's one of the reasons why I think eBPF is the future of networking. And yeah, it's very powerful.
It's the fact that we can just push logic into the network layer and just like, you know, we don't need to recompile the actual userland projects that we might not even be able to touch or anything like that. You know, like those things are, they could be physical boxes or whatever, but as long as we're sat in the data path somewhere, you know, we can have that logic sit there and we can do whatever we want at this point, like ultimate power.
In that example, I haven't looked at how you implemented it, but was it NLRI? I guess that information was probably passed using a map. So you could change that map contents and, you know, you can dynamically change the way that behavior is operating without changing the BPF program, you know, just dynamically changing the behavior.
So yeah, as it passes the update message, it goes to all of the fields that are part of the update message and it'll find that NLRI part of things. It will then take that and use that to look up in the map. And if it finds an entry for that route that's being added, it will change it to what the alternative is as part of that map. And I luckily managed to implement that just before this echo session actually started. So like 20 minutes before, I was drenched in sweat, like, oh, it's not working.
There were a few other people who said hello who I just want to quickly bring up. So hi to Ansel, hi to Leon, and our good friend Mark. Hi, nice to see you. And then Daniel has made it back. I know earlier he had disappeared, but now he's back. And he said, do we think that there will ever be a BPF parse HTTP helper? I mean, great question. I don't think we're the people to ask. I think maybe we need to ask people like Daniel Borkman about that.
It's a good question, though.
Yeah, I actually have an inkling that the answer might be no, because there's a preference to move towards K-funks and not add limitless helpers. So yeah, that might be the way it's going to go. But yeah, I certainly can see how, you know, in a decade's time, we might be thinking, well, what? Yeah, everybody passes their HTTP packets in eBPF. Of course they do. You know,
that's the done thing. I mean.
Yeah. Now we have already gone past the hour. There was one other thing that I wanted to quickly talk about. I'm not really going to talk about it. I'm just going to do a bit of a tease for it now, I think. So I talked about how, you know, when I was reading a file, I might have a 128K buffer that I'm reading, and there's no way I'm going to get the stack space to parse all of that. And in my advent of code using loops and BPF loops and tail calls, I was able to give myself enough kind of space, you know, in the sort of complexity space of the verifier and the stack memory, the kind of conflicts of those two things. I was able to parse my 1,000 lines of advent of code, which is not the same as being able to parse 128K buffer. So there's a bit of my brain going, yeah, I'm not really happy with that. You know, I've solved the immediate problem, but I haven't, you know, it could be a bigger problem. So I was talking with John Fasterbend in our team, who is the architect really behind Tetragon. And he pointed out that you could use a map. They, in fact, do this in Tetragon. They have an array map that they use essentially as a memory manager. So they use that as a way for eBPF programs to pull memory out of a map instead of just off the stack. And there is also his example of kind of proving that you can do Turing complete essentially by having a BPF timer pop on a regular basis, run a program, process some state, store some state after it's been processed, and then the next time the timer pops, you know, repeat indefinitely. So at some point, I am hoping to find the time to prove to myself that I could parse a 128K buffer if I put my mind to it with these kind of mechanisms that John's pointed out to me. So and I'm also gonna point out that in the Cilium and eBPF Day that is coming up in March that we mentioned earlier, John and I are going to actually be doing a talk about eBPF's abilities and limitations. And essentially, you know, the sky is the limit. There's a lot we can do with eBPF these days. You know, some of the limitations that used to exist a few years ago, they've really been either worked around or lifted. And John's had some amazing, I mean, he's been a big part of that process kind of in the kernel and in the use of that by eBPF tools like Tetragon. So I'm very excited about putting that talk together and showing some Turing complete code. So join us in Paris for that co-located event. It'll be really good.
Absolutely. Yeah.
We've gone well over time. Sorry, go.
Yeah, no, I'm super excited at the moment. I just like the power of eBPF at the moment. It's been nice. It was nice, you know, as I mentioned over the Christmas break, to have a bit of time to kind of see what, you know, is kind of possible. Because, you know, a lot of people, I guess, think that these are the sorts of things that you just generally can't do or shouldn't do with eBPF. But I don't know. Try and stop me at this point.
Yeah, and I mean, Dan and I both have incredible colleagues who've been building amazing things in eBPF, like protocol parsing in Cilium. You know, there's some incredible expertise around us. So yeah, very much enjoying learning from these amazing people.
Absolutely.
Fantastic. Right. So if you have any last minute questions, type them in very, very quickly, because we are over time. City has said, yeah, the KubeCon Paris, absolutely. And we are very excited about that. And and we had Rajib saying, hi, everyone. Big fan of eBPF. Welcome. All right. I think we've talked for more than long enough today. I hope people have enjoyed that. I hope people have enjoyed digging into the code. All the links are in the show notes, which are on HackMD. You can see it in that corner. So, you know, take a look at the code examples if you like, and get in touch if you have questions.
I apologize in advance if you do look at my code. It's it works, but it's not the best.
Fantastic. And David said very kindly, awesome session, thank you. And thank you, Daniel. Wonderful. All right, we'll end on that positive note. Have a wonderful weekend, everyone, and we'll see you next time.
Thank you.